Hello, thank you for inviting me to give this lecture for the SciTech team. It's wonderful to be here. I kind of feel sorry that I cannot meet you in person, but at least I can give you a talk about our research. I was invited to give 3 lectures here in Brno and think about SciTech, and I thought that maybe I'll just propose something that is focusing more on the technological developments and will be interdisciplinary, namely will combine some imaging, but also some technological studies, the development of the new devices that are useful in the context of the rehabilitation of blindness. So this is precisely the topic that I would like to present you today. So I'll tell how to design sensory substitution devices. Of course, I don't have one answer that should be followed, but at least I'll show you how we try to approach this question with some research we've done over the development of the device called Colorophone that has been proposed by Dominik Konstiński from the NTNU in Norway. But we are collaborating with Dominik already for some time right now, trying to develop this device. At the beginning, the goal was rather into applying the Colorophone as a way of studying consciousness. But then we get interested in the development of the device itself to the extent that right now I think the studies are focused rather on the usabilities of the device. And this is precisely the story that I would like to tell you today. So the sensory substitution is a very interesting effect that we can describe on the examples that I'll show you right now. So this is a situation in which, as you can hear, we represent the visual object, as you can see here, with a sound. This is a particular example of such a device. It's called the device. I'll tell a little bit more about this device in a second. But this, I think, serves as an example what I mean by substituting the information that is not typically accessible visually with the other sense. So over the lecture, I'll start with showing you a few examples of the sensory substitution devices and also tell you a few words about sensory substitution itself. Then I'll just maybe comment a bit on how the sensory substitution is typically investigated and what we know about how people who use the sensory substitution device experience them. But then I'll focus on the topic of interest today. So I'll show you how we try to develop a sensory substitution device and show you the Colorophone 1.0 version. And then we'll show you how we discuss the development of the device and we'll discuss how this process should be guided further. I will also show you some studies in which we use the different approaches to the usability tests, so from like more structured one into the less structured one, but all of them with the idea of developing the device itself. And then, of course, I'll tell you a little bit about what we concluded from the studies that we have done till now, and also what we are planning in the future in terms of the further development of the device that I'll just describe. So starting with the sensory substitution definition, so sensory substitution occurs when perceptual information that is normally accessed through one sense, for example vision, is represented by another sense. Usually because the sense, the first sense is not accessible because of some reason. Typically, this kind of devices are used in the rehabilitation of people who lacks vision or lacks the access to the auditory information. Namely, these are basically assistive devices that are developed in order to support the everyday life of blinds or deafs or otherwise disabled participants. So sensory substitution devices are typically constructed with 3 elements that will just, as you will show, as I will show you in a second, could be differently designed. So typically we've got a sensor that is basically providing and coding the information from the sense that's supposed to be substituted. So in the most cases it will be basically vision. So but it could be also some characteristics that we usually typically investigate with vision, and then they became a focus of the sensor and the a measurement that we are making. So the examples of those sensors that we use in these cases will be just camera, for example, or ultrasonic sensors. I'll show you some examples in a second. Will become more obvious. Then we've got, of course, the stimulator. So like the output of the system, and the output provides the information into the another sense, right? So in this case that is described here, there will be the auditory information. Thus we will have as headphones as an output. And then the most important thing is, of course, the coupling system, namely the system that translates the information from the visual one into the auditory one in the example that I'm just describing. So this is how this usually look like. So we've got like some kind of the sensor. So here you see, for example, the glasses with the camera. Then you've got like a coupling system, which is, you know, usually some kind of the either developed device itself, or this is basically a software on a computer or a mobile phone. And then we've got the effector or the output of the system. In this case, it's the headphone. And of course, the task is just to, and the reason why we develop this kind of the devices is basically to develop means to experience different features of the world that are otherwise inaccessible to blinds, for example. So you may think about obstacle avoidance, for example. So if the person is blind, then of course he can use the sensory substitution information to avoid obstacles. Of course, what blinds typically do is that they avoid obstacles with the walking stick, but then of course, like the distance that they can search through is like kind of limited. So sensory substitution device would allow them to broaden the scope of the perception and help help to navigate in the environment. Then you may think about the depth perception, for example, like defining the distance in between me and the object, motion detection, but also something that is related more into the somatosensory integration, which is like, for example, reaching requires perception, but also the integration of the perception with the movement control. So this is something that in which we'll go into more details in a second. Of course, you may think also about the object recognition, relative size estimation, location identification, and many other features that we typically experience visually, but then of course the idea here is to translate them into the information that is accessible auditorily. The problem is, of course, how to develop this coupling system, and this is something that I'll show you a few examples of, and then I'll tell a little bit more about the device that we are developing. So the most known and the oldest sensory substitution device is the BrainPort, is the vision tactile sensory substitution device that basically translates the information from the low resolution camera into the vibrations that were initially provided by the matrix, like the one you see here that was on a chair, and you felt this matrix on a back, then that was word on belly, and currently the device is just basically used on the tongue. And the way that the system is working, basically you've got like a low resolution camera, so that's 20 by 20 pixels. And this 20 by 20 pixels is just basically translated into the tactile stimulation that you can feel. So if you've got like effectors, like 20 by 20 matrix, and the lighter the certain pixel is on the image, the stronger you feel the vibration on this tactile plate. Or you can reverse the coding if you wish, but this is like a detail that is not of really interest here. So the thing here, what is important is that you provide information about the scene perception, namely about like the whole scene that is captured by the camera, but in a very low resolution, and also and with no information about the depth in a sense. But still the important thing is that this information are provided online, so you immediately, in a sense, perceive what is present in the environment, especially if it's very contrastive into the other object that you perceive in the world. This device allows object recognition as well, and is used in the multiple contexts. It could help like everyday behaviors. So here you've got like the example of the guy who's climbing using the BrainPort. But for some reason, even though the BrainPort is available on the market already for some time, it haven't been like broadly used, and we are actually right now running one of the studies in which we are just comparing the BrainPort with our device, and there are indeed some problems which we experience that are related with the usability of this device that prevent us. Probably might explain this lack of the popularity of the device. Of course, like the most obvious problems are the one that it's impossible to report what you see. So basically, whenever you got like this plate on your tongue, you need to remove it so to say something. So this is not like really user friendly. And then. It's of limited use, so it provides only information about the contrast in a sense, and the amount of light you perceive in your surrounding. The other device, just to show how differentiated are the ideas that people come up with, and of course I will not report about all of the types of the sensor substitution device, because as you will see in a second that each of the categories is like really broad. But here is just totally another way of thinking about the sensor substitution devices. So this time you do not represent the whole scene, but you represented only one feature of the scene that is not accessible otherwise to the blinds, namely the distance perception. And here the idea is that you've got a minimal vision to tactile sensor substitution device that make use of the infrared or ultrasonic sensor to provide information about the distance from the obstacles or other objects. So infrared or ultrasonic differs in the scope of the device. So if it's infrared, as you may imagine, it's basically measuring the distance into the object that is directly in front of the device. But if you're using the ultrasonic sensor, then the sound is just, of course, spreading as it's typical for sound. So then you can, for example, receive the information about the object that are not necessarily just in front of you. So then, of course, you can use the device slightly differently. But it's not like really crucial here. The crucial thing is that how the information is translated in the way that is available for disabled. And here you've got the coding. So the information is translated into the vibration strength. So you actually have like the wristband that you feel. that is vibrating, and it's vibrating usually the stronger the closer you're to the object. So it works slightly like a parking sensor in a car, if you wish, but with tactile stimulation instead of the auditory stimulation. This is again like the online device, so you can just basically search the information around, but provides like a very minimal representation of only one feature of the visual scene. That is of course important, but limited in the sense of the usability. And yet another and the last example of the device described in the literature that I thought might be good to show at the very beginning is the voice system that has been further developed by the Amedi as an iMusic system. So both works in a way that you can see here. So we've got the vision to auditory. We are talking about the vision to auditory sensory substitution device that is making use of the regular camera, but because it aims at representing the scene perception, namely not only like the one point in a space, and not the scene itself, but the very low resolution, then because of the computing requirements, basically the device is capturing a scene. So you've got like a static image that is like a kind of the photo that you're making in a place where when you think and you would like to use the device, and then you hear the sound that is representing the scene, and this, because it's static and it's offline, you can use time as one of the feature of the translation of the visual stimulation into the auditory information. So here is like the visual representation of the coding. So the louder the sound is, the brighter the object that you that is represented you hear. Then the pitch represents, so the high pitch are on the upper side of the scene, and the lower sounds are on the lower side of the scene. And then you've got the time and the stereo panning from the left to the right. That represents the horizontal position of the object, right? So if you see something in the upper left corner, then you hear a high pitch at the beginning of the soundscape. Let's call it this way. And if you present, like for example, the object on the bottom right side, then you hear the silence at the beginning, and then you hear the with the delay you hear the low pitch sound on the right headphone. So this is how the information is coded. So this allows us to represent much more complex stimuli. So for example, you can imagine the stirrs that will be just increasing pitch over the time, or decreasing the pitch that decreases over the time, just to represent like the line that is going this way or the other way around. You can imagine like the representation of like objects of the different brightness. Actually, the further development of the device by Amedi allow also to represent the colors. So they provide the sounds that represents 5 main colors, and you can hear the sounds depending on the color, representing not only the position of the object and the brightness of the object, but also also the color of the thing. But it's all happened offline, which is of course kind of the problem if you want to use it in the direct interaction in the world. The development of this device is still taking place. So there was like the one of the versions from more or less 10 years ago look like the one that you see here. So you've got like glasses with the camera, and then you've got the headphones, and you had like the PC notebook hidden in the backpack of the participants. Now it's miniaturized in the device you see here. So you've got the headphones, but the camera is within the glasses, and the computing unit is inside as well. So you do not need to use any anymore. Here you've got a list of the further systems that has been described in the literature. This is a part of the review that we made in the paper we recently wrote with Dominik Osiński from the NTNU. So here are like only the some examples of the color to sound sensor substitutions, and as you've seen before, we have also color to tactile stimulation, for example, and there are of course much more options you may think about. And here you've got the information about how they are constructed. So you've got like the information whether the camera is integrated, whether they perform the information about the scene in a real time. So here you've got the iMusic that so the new version of the voice that I just described. As you can see, the real-time processing is not available at this one. And then we've got the information about the specialized sound, namely whether you hear the things that are on the left in the left channel, and things that are on the right channel, as you can see in iMusic is implemented. So as you can see, those on the market, there is a lot of solutions. Some of them has been patented, some of them are still being developed. None of them is actually broadly used for multiple reasons, depending on the device that we are talking. Some of the devices are not popular because of the price. Basically, they're very expensive. Some of them are not user-friendly. I do not want to say nothing bad about any of those devices, because this is not like really an idea that's then behind us to criticize the others, but rather we thought about some other approach that we can take to developing this similar system, and I would just like tell you the story how we do that. But before going into that, also I would like to make a short note on why sensor substitution is interesting from the empirical point of view and from the basic science point of view. So firstly, these are like two main reasons why we do the SS studies. So firstly, of course, as I already mentioned, it is used in the context of the rehabilitation of the blind. So then we, of course, mainly interested in the performance or the accuracy of the various tasks that we may think about with the use of the sensor substitution devices, just to show that people are better in using or navigating or behaving in the environment with those devices, namely that basically the devices are helpful. And the other thing that is kind of related with that is, of course, how likely is that people actually want to use this device, and for this purpose some of the devices are being compared. And here's, for example, like the study that basically shows that the pleasantness of the usage of iMusic is much higher than those of the voice device, because of some technical developments that have been made over the way. For example, like the sounds that are much nicer in the iMusic than in the voice, which basically shows that those kind of studies are focusing on the usability to the more extent. But we also have got like this lines of studies that are investigating neurocorrelates of sensory substitution, and this is very interesting because what is quite often observed is that the prolonged usage of the sensory substitutions resulted in in neuroplasticity. So actually there is a huge difference in the brain activation in reaction into the meaningful stimuli that has been trained over and observed thanks to the training in the sensory substitution. As when you compare before the training and after the training, you see that the activation of the visual areas appears for the stimuli that has been provided in the substituting modality, namely they react with the activation, like participants react with the activation of the visual cortex for the auditory stimulation. Of course, it opens like a question of how this actually feels to experience those sounds. So if the visual cortex activates for the auditory stimuli, does it mean that this is became like an experience that is similar to the sight, or whether it is still like the audition, but basically providing the additional information that are decoded by the visual cortex, or whether we are building some new modality in a sense. So this will be actually from the point of perspective of the study that we are running in our lab. At the very beginning, it sounds like the most interesting area of research, namely if it's indeed the case that people are forming kind of the new type of the experience that is uncomparable neither to the substituted modality or the substituting modality. This means that we are actually dealing with development of the new experience, and thus we can actually observe how people form the experience over the training, which is something that is typically not available because we do not have an access to, like typically we do not have an access to the people who start using their visual system from the start, right? This is not accessible, so actually the possibility of developing a new sensory modality thanks to one of those devices sounds really interesting. And imagine that it could be actually, us trying to understand how bats perceive the world. So as we all know, the bats perceive the world with the echolocation, but what is kind of problematic here is that we cannot like really imagine how it feels like see the world through the echolocation. So what these devices are providing, the opportunity to see how it feels to experience the world, for example, with the echolocation or with the other type of decoding of the sounds that you may think about. So this is the state of the art, and this is also the starting point of our collaboration with Dominik Ostrzyński. So we were firstly Dominik found himself like the first version of the device, but also later, like really at the very beginning, we were lucky to meet him at the very beginning of this route. We start to discuss what are actually our assumptions about how this new sensory substitution device, if such a device will be built, should be constructed. Because Dominik is an engineer, he was thinking also about some practical issues. So actually one of the first things that I should mention, which is actually not on the list on the slide that you see right now, is that Dominik constructed the device that will be broadly available. So it will be actually cheap, easily accessible, and easy to use for like people all around the world. But we also got some further assumptions that relates to the features of the device that I described so far. So firstly, we thought that device should definitely work online, so should be like real-time feedback. So we shouldn't like think about any scene perception in which we just make a photo of the world and then like reproduce what has been represented at the scene. Then the system should be intuitive and user-friendly, as I said, and should be should reduce the number of the information from the environment in a sense that it should be useful, and it means useful whatever feature of the environment you got in mind, you need to reduce the number of the information, especially from vision, and this is of interest here, to be able to actually decode it effectively, meaning that it will be useful in the context of some task performance, for example. And you will see what we mean by that in a second. And then the last thing that is worth to mention here is that and this is the Dominic's idea that we still discuss, and I'm not really sure whether I fully agree with it, but Dominic's approach is that the device should substitute the missing function, and by function understand like really like low level way in which the substituted sense is functioning. Namely, in case of the vision, we should in a sense try to reproduce the way in which the visual stimulus is processed, so to code it in a similar manner and only then translate into the auditory, in this case, information that will be presented into the participants. So these are like the starting point assumptions, and here is like a first version of the coloraphone that has been developed over a few years now. So that the very first version of the coloraphone has been described in a paper by Dominic and Doug in 2018. So this is, but actually they have constructed it slightly earlier. So we are talking about the visual to auditory sensory substitution device that is making use of the camera, and it translates information about the color into the sound. As you will see, it translates the color not of the whole scene, but of the small square in the middle or in the fixation point. But the important thing is the coding, so how the colors are represented, because the idea here is that we shouldn't represent like very only simple colors, so we shouldn't reduce the number of the colors that people may perceive, but actually we should build a system that mimic in a sense the way that the color perception look like, and basically construct the color perception from the beginning from some coding system into the representation that will allow us to perceive the whole palette of the colors. So how this is done here, we've got like what the website of the thing, if you will be interested in more details. How does it seal thing? So we've got like three sounds that represents three main colors or in the RGB palette. So we've got red, green, and blue, and red is the high tone. So here's how it looks in the implementation on the Android. Here is the red sound, green sound, blue sound, and then white is coded as the white noise. The gray is basically a little bit more quiet. Purple is just a mixture of the blue and red, and the orange is the mixture of red and yellow actually, but this is another type of decoding that I haven't mentioned, so let's forget about the last tone you have heard. As you can see with this example that I just presented, many things are changed here and developed over the time. So the coloraphone one described in this paper is not like really the same device that we have used in the tests in the study that I'll just describe in a second. But the way it functions was more or less the same for all of the time. The things that we were changing was the palette that has been used. So I just described and will continuously describe the way that this system works for the RGB palette. But there is also a YGB palette, so the one that includes the yellow as a separate component of the color perception, and such a palette has been used in the development of the coloraphone in some cases as well. And the further development is of course like this application, so it uses the same the same rules for each and every implementation. But this is a version of Android, but we have also used the earlier version that works only on Windows, for example. But this is not like really important for those things that I just want to describe you today. So this is how the coding look like. And then if you think about what this device allows you is that firstly, of course, the device allows the color recognition, because of course, as you can imagine, if we've got these three basic colors from the RGB palette, then you can mix them to, as in the violet example, that is basically a mixture of the red and the blue. You can represent any color you may think about by just a mixture of these three simple stones that you have heard at the beginning. And of course, like the proportion of the colors is represented by the proportions of the sounds. So we manipulate the loudness of the volume of each sound, and basically the louder it is, the higher the volume, the more of the color component is coded. So this way you can quite easily and naturally, and especially naturally, use learn the association between the color and the sound. This is really easy to learn, and especially easy to remember, in a sense that you do not need to keep in mind like the information about like some thresholds or the colors in between the colors. You just need to remember three simple sounds and then just try to reconstruct like the components into the color that has been actually presented. But also this color phone device allows the shape recognition, if you think about it, because because it works online. So if you've got like the square and the meaning of middle of the visual field, then of course you can move the device, which is actually placed on your head. So that means you move your head and you may, in a sense, scan the scene, trying to recognize the object thanks to the sensing motor contingency. So this is how it looks like. So here you've got like this small square, hopefully that is visible, and you hear online the, oh, this is yellow, for example, this is white, yeah. And of course it works online, so you can actually associate the changes in the auditory output with your movements, so to detect the position of the color for objects in the scene. Okay, so this is how it looked like, and then some proofs that it's actually working. So here is like a very simple task that is quite often used in the context of the studies investigating perceptual awareness. So you've got like the four shapes that can be presented, so circle, square, triangle, and diamond. Then there are masks, which is not of importance here, because in case of the visual perception, we need to like make this task slightly more difficult, which is not the case for here, because of course it takes some time to develop the fluency to be able to recognize it immediately. But then the idea behind the task is as follows: that you present the fixation point, then you present the object, and then you ask people to respond which of the objects they've seen, and then they are asked to respond on the 4-point scale to how clearly they saw the object, for example, or in this case, how confident they are that the object was which object was presented, right? So whether they are confident in the response that they just gave. So if they are not confident, they're going the guessing response, and if they are confident, they go giving like the higher, like 3-4 responses. So one is guessing, two is not sure, 3 is almost confident, and 4 is confident, let's say. That's, for example, these are the labels you can think about in context of this scale. So what we have here is like a typical results we observe with this kind of the paradigm. So if you combine the data from many trials of this kind, what you usually see is that some trials, especially because we have introduced this manipulation of the presentation time, so actually some trials are perceived easier than the others. But what is important here is that the more accurate people are in detecting the object, they're also the more confident they are in what they see, right? We will show basically they have an access to the information about the shape of the object. And what we did, we basically try to replicate this effect with the colorophone. So this is how it looks like. So this is the very first version of the colorophone that Dominik Osiński has proposed. And we've got a movie here in which you can see how the 4 choice recognition task look, right? So we've got the object that is present in the screen. So here is the green triangle, and the person, as you see, is moving her head so to scan the object, right? And then so to recognize the shape of the object of interest here. Yep, so you see the movements and what person is learning to associate the movements with the sounds, changes in the sound she heard. So as you remember, the green is a middle tone, the black is basically no sound, and the white is a white noise. So she should try to find a focus on the quiet area, let's say, and then to detect the shape of the object that is presented in the middle. So what we have found, we found that participants are, so here you've got like the view from the camera, right? So you see this square here that is allow a person to scan the shape, and as you can see with this view, she's able to control the position of the square quite effectively, in a sense that she's not going behind this black square that is visible here. And then what you also see on this graph is the relation in between the accuracy on the logit scale, doesn't matter, and the confidence, as in the case that I've shown you here. And what you can see here is that this relation that we were expecting, in which they give the higher ratings of the confidence when they are also more accurate, is true for like a square, which means that they are very good in recognizing it and they have an access to the information on that. Then this is also the case for a triangle, and to some extent for this diamond, which is slightly more difficult. But over the training, they haven't learned actually to properly access the information about the circle, right? So in a sense, it seems that they do not have an access to the information about the circular shape, which is to some extent to be expected, because actually detecting the edges of the circle is the most difficult. So it's often mixed with one of those other shapes that you have seen. Okay, so this is one thing, and this is also these are also the results that shows that the device allows the color perception. So here we've got the simple color recognition, which is no, we don't have it. Sorry. So this graph presents only the complex color recognition. So we've got the cyan, which is in red. Sorry for that. The purple which is in brown, the olive, which is more or less in olive, the magenta, that is blue, and then yellow and teal. Never mind, what you can see is that there are also some colors that are better in recognizing. For example, like olive was like relatively easy for them, and also this applies for the yellow, and this applies also to some extent to the teal, but it was not the case for example, like a purple or cyan. Nevertheless, it seems that the general the general goal has been achieved, namely people were able to detect colors, at least some of the colors, because of course they were very good in detecting the simple colors that is not represented here with the device. After actually very short training, because the whole task together with the training in those first pilot studies we have run was like about 1.5 hours. So if you think about it from this point of view, the fact that through the 1.5 hour people were able to detect objects accurately with the device, and that also represents quite simple and some of the complex colors already, it seems that the device, it's promising. But of course, like, the problem is that we should go into more details, and to go into the more details we need to organize the nightmare study, let's say it this way. So basically you need to organize a study that is prolonged, so into the extent that people can actually acquire the ability to use this device. So we need a long-term study, and we have tried our best to organize such a study. That was like long-term repeated test in which we ask people to use the sensory substitution device. The idea is that the initial idea we had is that we supposed to have like a relatively large group of the participants. So that's why we have recruited like the cohort of the 16 of them, and actually the initial plan was 30, but then firstly, as you will see, that the results are not like 100% conclusive, and I'll go into that in a second. But even more importantly, the pandemic hits, and we basically were kind of forced to stop that collection at the time. Nevertheless, just coming back to the very idea of the main study, we've got like long-term training. The idea was that we're supposed to train them on the everyday basis, and because of the fact that it's just impossible to invite 16 participants every single day into the lab to provide them with some training, then for 3 months, then we basically developed like the virtual reality environment that allows us to train them at homes. Of course, we were testing the performance of the participants from time to time in the lab, and we also monitored the changes in neuroplasticity over the course of the training. So here is like the very complex graph, but that will basically show how the study was organized. So here you've got the weeks of the study. So in the first week, we've got the MRI test. Then we've got the test at the lab, namely the test in which we were checking like the starting point of their availability to make some easy perceptual tasks that I will just describe in a second at the beginning of our training. And then starting from the day 2, so already in this week, participants start to use so-called VRCO, so the virtual reality system that reproduce the colorophone functions. And then this VRCO has been used for 2 weeks exclusively. Then we've got like another meeting with the participant in the lab. And then we again run 2 weeks with the VRCO training only. Then we've got the first post-test of the MRI to see like the short-term changes in the brain activity. Then we've got another meeting in the lab, then another 2 weeks of the training with the VRCO at the participants' homes, another measurement at the lab, and so on. So for us, you can see with the third measurement of the MRI and final text at the laboratory after 3 months, and then we've got like also the follow-up tests just to see whether the effect is preserved or over the time. So whether the neuroplasticity has stayed even when people were not training, or still observed even if people are not training anymore. So as for the MRI, we have some sessions in which we check the reactions of the people into the sounds that were meaningful, namely the sounds that were associated with the certain colors. So we present like the sound that represents the colors that are used by the colorophone, and then participants were because of the we want them to keep attended to the task. We ask them to react to the audible sounds with the button press, right? So they were like passively listening to the meaningful sounds, and then they react to the audibles. So here is the description of how the test looks like in the lab. So we've got the fixation cross, then we've got the object people supposed to recognize, and they scan it for 40 seconds. And then we present them with such a stimuli, so they've got a line in the middle and the object on the left and the object on the right, and people supposed to scan both and say which one has the same orientation as the one here. This is a task that actually allows us to control the difficulty. So at the very beginning, the difference in the orientation was massive, as the one you can see here, but then over the time we used the staircase, so the better people were in this task, the smaller the difference was in between the orientation of those two objects. So this is like the orientation detection task and actually the object detection task at the very same time. And here is the second task that we have used, namely this is the object detection task. So that was always a circle, but the circle was hidden in the noise. And the task of the participant was to say whether the object was presented or not. So the stimulus was presented with the fixation cross, similar to this thing here. This fixation cross looks slightly different in the sense that it's red and then it got this green dot in the middle. This is because we need to make people focus in the middle of the cross before they start scanning. This is how we ensure that they are actually looking on the part of the screen that we want them to look at. And then the most, I think, interesting part of this study is that this virtual system, so this is like the virtual reality environment in which we allow participants to explore like a different environments in which they may find like objects of the different shapes and colors, and also the rooms themselves got the different shapes and colors. And the task of the participants was basically to for 12 trials each day to detect the color of some objects and for 12 trials to detect the shapes of some objects. It was done in the virtual reality with the fixation on the correct responses, so the responses were collected in the virtual reality. And what is important for that is that we increases the difficulty of the task that has been provided to the participants over the time, assuming of course that this training will contribute to the accuracy in this task, and also result in the neuroplasticity as observed in the MRI. So in other words, we are just basically structurizing the competences that I've just described before. So we are just like checking whether people are indeed able to recognize objects and recognize colors with the device. But also we were also interested in the mechanism that is just behind. So we were studying to what extent the color of font has been actually has actually changed the way that people are perceiving the world thanks to this sensory device that they got an access to. So here is the representation of how the vehicle look like. So here you've got the very same setup as in the real studies, but this time you've got the fixation point, and you can scan the scene also with the movement of your eyes, of your head, right? So this is exactly the same sensory motor contingency that you're learning. Some people are just basically moving their hand and their head, and they're scanning the environment, trying to detect the colors and the shapes of the objects that they can see around. And of course, we have started with much easier environments. So there was, like, for example, one wall of a given color without any additional objects, and the task was to recognize the color of this one wall, and then we complicated the tasks over the training, so to people acquire new information. Yeah, so this is how the task look like, and also how the responses look like. That was also implemented at the Android, and people use the virtual reality headsets to put the color the phone into, and then they scan the environment, and the position of the phone was tracked with the gyroscope and the other functions of the mobile that could be used. Phone that can be used for that. So here, like to make long story short, here like the basic results. So we haven't found actually much progress in the vehicle, but this is to be expected. And there's also huge variability in the response here, as you can see, both for color recognition task and for the shape recognition task. Actually, it seems like that there are even, sometimes worse, but this is again to be expected because the task became more and more difficult. Of course, we try to progress in the time in a way that people were able to follow the task, but sometimes it seems that we just designed the tasks that were slightly too difficult for the participants. More interest, but this was here we haven't expected any changes here, so this is more or less the thing that we expected. The only thing that is kind of surprising here is that the variability which shows basically that people behave in this text very differently, and here is the results of the task in which we actually should observe some effects. So these are like the staircase effect. So here is the orientation difference. So here the larger the difference, the easier the task. So we expect that it would just drop down like that. And as you can see, this is not really a case. And again, we've got like this huge variability present, and this is the object detection, and here the results are even less, I would say, conclusive. Here we saw some trend into the increased accuracy, but I think that is mainly because like this drop from here to all others, right? But then actually we do not see much progress over the time on the group level, of course, and this is again something that I will just come back in a second. On the group level, we also control for like the brain activity. Then actually we saw some effects in between the sessions. We are still discussing how this should be actually calculated, but this is like the current version of the results. And what you can see here is that we've got the activation of the visual areas to some extent, but actually the whole network that is related in the sensory to contingencies, right? Which is kind of interesting because it shows that it's not like they represent the object visually, but they rather acquire some motor contingencies that allow them to do the task. So they rather not experience this object visually, but they basically act, and this act was kind of more important for them to run over the task. But these results are not very conclusive, mainly because and I will not go into the details in this table, but this shows that the variability of the task performance is very large. And actually we can even in this group of the 16 people see some of the people who progress over the time in the task that we run in the lab, and some that actually seem to even regress in it, in the sense that they were not good at performing that, neither the Virco task or the lab task at all. And this is quite surprising, and also it makes us think to what extent it is actually possible to design the device that will be useful to the same extent to all participants and all users. Just to conclude, before coming into this point about the individual differences, again, the color of our font seems to enable us to reproduce the typical data from the studies investigating conscious perception, as has been shown in the pilot study, and also to some extent in the study that we are describing right now, because the training was not visible, but actually they were able to perform the task above chance, which is not actually visible here, but still they were doing so. So the staircase was set up at around 70% accuracy, so they constantly run the task above the chance level. They basically haven't progress on this task too much over the 3 months that we have trained them. Then, as you can see, we have investigated the effect of training that maybe haven't got any results on the behavioral level and on the group level, but that clearly shows some effects on the individual level. So some people clearly learned something, some people clearly weren't able to learn nothing, and also it resulted in the changes in the brain activations, and especially in the reaction of the sensory motor network into the into the interpretation of the signal from the sensory substitution device. Finally, and coming back to these individual differences which are of interest here, definitely it seems that it might be this device will be useful only for some small fractions of the participants, and maybe we actually designed this device only for the small fraction of the participants. So we start to think that actually we should think about the whole thing in a more complex manner, and this is the work and the idea of Marta Łukowska, who is a leading author of this paper that I'm just reporting you right now, and then we are planning to submit hopefully quite soon. The idea is that we shouldn't rather think about SSD as something that is also the technological challenge, but the SSD should in a sense compromise the technological developments, the possibility of the and opportunities to interact in the environment, but also the needs of the users, right? So depending on what user would like to use the SSD for, it should be designed differently. And here you've got this individual differences that should be somehow reflected in the development of the technology. You've got this difference in the environment that should somehow influence the development of the technology as well. And of course, we've got the interaction in between the user and environment that we should take into account as well, because this interaction should be supported by the SSD that we are developing. So this is kind of the moment at which we change our mind on how this sensor substitution device should be developed, and we are also thinking right now of how to take into the account those different ways in which the user may use the device. But we are also thinking about like providing basically more functions for the device, and here are like two colorful developments that has been proposed after the study that they have just described. So the first one is the one that focuses on the depth perception, and the second is focusing on the scene perception, and I'll present you both very shortly. So as for the depth perception, so this is a concept of so-called visual echolocation that has been developed by Patricia Bizan-Angov. So here is the idea is that we are using the stereoscopic camera to represent the information about the distance. Then there is quite complex algorithm that transform the information about the distance from the object right now only in the virtual environment for the technical reasons into the depth maps. So actually because of the stereoscopic vision, we can estimate the distance in between the agents in the virtual environment and the object, and then it is transformed into the sounds according to the rules in which the virtual the colorophone is working. But then you hear the objects on the left in the left channels, and the objects more to our right in the right channel, right? So here is the representation of the sounds. So here you've got the right channel, left channel, and you've got like a red, green, blue, and white noise. And what you can see here is that we've got the activation of the red more towards left, and then we've got the activation of the green more in the middle, then the activation of bluish more into the right, and then the activation of white noise channel even more to the right. So this is this object, right? So you've got like a red object, then you've got the green object, then you've got the blue object, and then you've got the white object. And this represents the distance, right? So you shouldn't take into the account this color as the color of the object, but rather the color representing the distance. And here you get the scale. So because of the stereoscopic vision, we can decode in the depth map that this is closer, this is slightly farther, that is even farther, and this is the object that is in the largest distance from the perceiver. And the same algorithm on something more complex. So here you've got like the staircase. Again, this is only run in the virtual reality. So you've got the stairs and some wall on the left. So this is transformed into the depth map again that you can hear. So here is something that is very close, and then you've got like the distance that is increasing, and then you can again hear it here. So you've got the information about you see on the left channel, in the white channel. You hear the wall, right? That is here, and it's louder in the left channel than in the right channel. And then you've got the in the red channel you see the steps, right? So they are like steps in the left and in the right channel that represents the position of the object in space, right? So the farther the object, the later you hear it. I guess I haven't sounded it, so this is the time, of course. So the earlier you hear it, the closer it is. The later you hear it, the further it is, as you may expect, given the name of the solution, namely the visual allocation. And these are some very basic usability studies that rather are thought as a proof of concept that is indeed people are able to almost immediately recognize the scenes that I had just presented to you. So they're like good in detecting of how many of which colors objects were there, and also about estimating the distance of those objects. So we basically played the sounds into the three testers, and as you can see, they're responded to most of the questions like as expected. So this is the results for the scene 1, and as you can see, they responded. So this was the question about the object on the right, and the correct responses was white, and as you can see, they all responded as they supposed to. And so on and so forth. If you're interested into the details of this test, you can check our sensors paper that report the study together with presenting and also and most importantly present the idea itself. And then the second development that I just want to mention at the very end of this talk is just so-called Coloraphone 2.0. So here the idea is that we of course developed device massively since then. So for example, as you can see, that you probably do not see the headphones, but it's using the bone conducting headphones that are hidden into these glasses that you can see here. So actually people can hear what is happening on the street, but at the same time that they can use the Coloraphone device. Then we've got the camera that is attached to these glasses. But most importantly, this time the Coloraphone has been designed in a way that it's not only representing the information about the color of the object in the middle of the scene, but it's representing actually this stripe of the colors, which is vertical, and then each of this area that you can hear here is heard at with the specialized sound. So basically this sounds as being more on the left, and this sounds like being more on the right. Namely, this sounds in the left channel, and this sounds in the right channel, and this sounds in both channels. So if you use the specialized sound solution, it sounds like you're able to detect on which direction the object is. And this is something that we are just working on it right now, developing the device and actually extending the way in which it could be applied. The paper is under the preparation, so I'll not go into the more details maybe before we'll not just describe it. Also because I'm not really sure what will be the final implementation that we'll just use in the paper. So as you can see, we not only changed the methods that we are using, but also the approach to some extent. So we are just trying to think about the features that might be useful for the users. And of course, scene perception is something that they quite often report that they would like to experience. And the depth perception is important for lights as well, because they both represent the processing of information about the external space. So something that is not reachable either with touch or even with the stick that they typically use for navigating environment. Of course, we've got also some follow-up plans. So we are thinking about developing the solution so it will account for the perception of the color in the context. So you're probably aware that we perceive the color not as it is in the environment, but of course we are perceiving it taking the account the color of the contextual cues. And this is something that is related with the top-down perception functions and haven't been implemented in the Coloraphone so far. So we've got the idea that we would like to develop the device so it will take this to the account. For example, to allow blinds to experience some of the very simple visual illusions. And of course, we are focusing more and more, as you can see also on the examples I have shown you, on the usability tests and the personalization options. And I think that this is the way to go if you would like to develop the device that will be useful for the final users. Thank you for your attention. Hope that you found it interesting, and I encourage you to contact me if you've got any questions about the solution we have proposed, or you've got any suggestions on the direction we may follow in our future studies developing the system that I've just presented to you. Thank you for your attention. Thank you to Dominik Osiński, who developed the device to collaborate with us on that for quite a long time already. This is the grant that we received to develop this device from the National Science Center. And here is my research group from Consciousness Lab, without whom all of this would not be possible, and also the link to the newly founded Center for the Brain Research. We still do not got a website ready, but you will see it there quite soon, because I hope we'll air it somewhere next month. If you would like to contact me, please visit our website. I'll be happy to respond to any questions and comments. Thank you for your attention. And thank again, Milan, for inviting me to Brno. It was a pleasure to be here, and I hope to visit you again, hopefully this time providing the lecture in person. Thank you very much. Goodbye.